In this lecture, we're going to concentrate upon series. A series is a finite series if you're adding up a finite number of terms. It's an infinite series if you're adding up an infinite number of terms. Now, for a finite series, sometimes you can just calculate the sum by adding one term to the next until you get to the last one. In an infinite series, you cannot do that because you have to keep on adding all the way up till infinity. Sometimes we are able to do that analytically, and we'll do that for the case of the geometric series, but most of the time we'll be interested in one question. If you keep adding up the terms of an infinite series, will it all add up to something that is finite? Or is it something that is either infinite or undefined? So the question of series, the convergence of series, is what is going to concern us here. Let me begin with a couple of examples of series whose sum one can actually calculate. Normally, an infinite series is difficult to sum, but for the geometric series, that will turn out to be possible. A geometric series is of the form 1 plus r squared plus r cubed. So each term divided by the previous term gives a constant factor of r. And here, I will insist that r be strictly less than 1. And of course, each term over here is positive. So r is positive and less than 1. You can see that if it is greater than 1, that this sum will then go to infinity, it will diverge, and we won't be interested in that at all. Now, instead of considering the infinite series, let me consider the finite series, which has a last term to it. So 1 plus r squared plus etc. all the way up till Rn, capital N. And we denote this as n equals 0 up till n, r to the n. Now let me multiply this with r, and this becomes r plus r squared plus r cubed, and then I'll get Rn, and finally r to the n plus 1. Okay, so now I can take the difference, Rsn minus Sn. So I simply subtract from this, and of course everything will go away except r to the n plus 1 minus 1. So you can see that this will cancel against this with this with this, and so we're just left with this. And so from here, Sn, if I take that common, into r minus 1 will be equal to r to the n plus 1 minus 1. And so I've got from here the value of the sum Sn all the way up till n as being 1 over 1 minus r to the n plus 1 divided by 1 minus r. Now, as n becomes larger and larger, goes to infinity, Sn then is going to tend towards 1 over 1 minus r. And this is then going to be the sum of this geometric series. This is, over here, the remainder that is left over when we sum up till n. But you can see that since r is less than 1, therefore, as n becomes larger and larger, this term over here will go to 0. And so, the sum of an infinite series, a geometric series, which we'll call S, is then 1 over 1 minus r. And now that's an important result. So in terms of what we've learnt in terms of sequences, we had S1, S2, S3 all the way up till Sn and then beyond. So that was our sequence. The sequence is clearly converging to this limit over here. There's another series whose sum we can calculate quite easily. It's called a telescoping series for reasons that you'll soon see. Here, the basic observation is the following. I can write 1 over n into n plus 1 in a slightly different way. 1 over n minus 1 over n plus 1. You can just check this. Now, instead of considering the infinite series over here, I'm going to consider the finite series, which means that I will go only from n equals 1 up till capital N, and then I will put in 1 over n into n plus 1, which can then be written in this manner. Now, what is this equal to? When n is equal to 1, I have 1 over 1 minus 1 over 2. When n is equal to 2, I get 1 over 2 minus 1 over 3. Then when n is 3, I get 1 over 3 minus 1 over 4. And now this will keep going until I reach the last term. And there is a last term because this is going only up till capital N. And there I have 1 over n minus 1 over n plus 1. Now you notice over here that there's a minus half and a plus half. So this and this will cancel. The minus 1/3 and the plus 1/3 will cancel. The minus 1/4 will cancel with the 1 out over here. And this too will be cancelled. Only this term over here will remain. And so we have an answer to this. It's 1 over 1 minus 1 over n plus 1. So what we have now is a sequence Sn where n goes from 1 onwards, and as n becomes larger and larger, you see that Sn approaches 1 because this over here goes to 0. And so the infinite series, this over here, let's call this S. This has value 1. So this was another series which we could successfully sum. Moreover, we established the convergence of the series because this is a sequence which is tending towards 1. We've just seen 2 examples of infinite series that actually converge, and we've been able to calculate their sums as well. But lots of series like this one definitely diverge. Can we say when they will diverge? Well, one condition is perfectly clear. If the limit of the terms inside is not 0, then this series will certainly diverge. So, for example, if I have an equals n squared, then the sum of an will be 1 plus 4 plus 9 plus 16 plus, and it'll keep increasing. The more terms I take, the bigger this sum will become, and so it will diverge. Certainly, if an is not 0 as n goes to infinity, then this will diverge. But if an does go to 0 as n goes to infinity, that is not enough for convergence. And we'll see an example of that right away. It could be that this series diverges because some partial sum is unbounded. Let's see what that means by taking the example of an equals 1 over n. Now, as n becomes larger and larger, certainly an goes to 0, like over here. But let's look at what happens to the series. So let me take the sum of 1 over n as n goes from 1 up till infinity. Let me write out the first few terms. So this is 1 plus 1 over 2 And then there's 1 over 3 plus 1 over 4 plus 1 over 5 plus 1 over 6. I'm sorry I have to write out so many terms, but it's going to be necessary. 1 over 8, 1 over 9, etc. Now, let me take the first two terms, these two. Then certainly if I add 1/4 to 1/3, I'm going to get something that is bigger than a half. Let me take the next few terms. Let me take from here up till here. And so that's 4 terms. One of these is 1/8. The others are bigger. So this is certainly bigger than 4 into 1 over 8, which is a half. And now if I had space over here, I would have again gotten something that's bigger than a half. So what I'm adding up is a number 1 plus a number half plus something that's bigger than half. I'm just going to write it like this, bigger than half, plus something again that's bigger than half, and an infinite number of terms, each of which are bigger than half. So this then becomes larger and larger as I include more and more terms, and so this goes to infinity. So what we've discovered is that this series over here diverges, and it's diverging even though this an, which is 1 over n, is actually going to 0. So what we're seeing actually is that these partial terms, each one of them is bigger than half, are adding up together to make something that is unbounded. Be sure to remember that n equals 1 up till infinity of 1 over n is divergent because we're going to use that fact again and again. Let me now pose the following question. When does an infinite series like this converge? Now this is a series of terms, Bn, each of which is positive definite. The answer is that this series will converge if it can be sandwiched between two convergent series. Let me explain what that means and prove the statement as I go along. So, this is a series, a1 plus a2 plus a3. Each of these terms is positive definite, and you keep adding this. There's no last member, but it converges. It all adds up to some number a. And this is, of course, what you mean by n equals 1 up till infinity of an. Now, let me take another series that's made up of C1 and C2 and C3, and all of these add up to some other number. Let's call that C. And of course, this is the summation of n equals 1 up till infinity of Cn. Now let's say that there is this sequence B1, B2, B3. B1 lies between A1 and C1. B2 lies between A2 and C2. B3 between A3 and C3 and so forth. So if I add these up, obviously I'll get something less than A and something that is bigger than C, and let's call this B. So this over here is n equals 1 up till infinity Bn. The condition that I've put over here is that each element of this sequence, Bn, is less than or equal to An, and it's bigger than or equal to Cn. So in that case, this B is sandwiched between the sequence A and the sequence C. So therefore, this sum over here is going to be bigger than this sum over here, but this sum over here is going to be bigger than this sum over here. And of course, the equal to sign can be there for certain cases as well. So I think that's pretty obvious then, that if this series converges and this series converges, the B series has to also converge. Now, of course, we could always choose, if we like, Cn equal to 0. So if we choose the sequence An such that Bn is lesser than or equal to An, in that case, the fact that A converges means that B will converge. Let's take an example of this. So let me choose An to be 1 over 2 to the power n. Now we certainly know that the series 1 over 2 to the n will converge because this is the geometric series. So if we start from 0 up till infinity, this over here will converge and it'll give 1 over 1 minus a half, which is 2. Now, if I have the sequence Bn, let me invent one just to see how this test works, which is, let's say, 1 over n to the power n. You can certainly see that n to the power n is going to be bigger than 2 to the power n, and so 1 over n to the n will be less than 1 over 2 to the n. And so what we have is Bn is less than An. And so, if we ask the question, does 1 over n to the n converge or diverge? We have the answer, because 1 over n to the n will be less than 1 over 2 to the n, and that's 2. So therefore, this series over here certainly converges. And the way we prove the convergence is we compared it with a series that is known to converge, and this other series, the convergence series, was bigger than the series that we were comparing it against. The sandwich or the comparison test can actually be very useful for helping us decide whether infinite series converge or diverge. So look at this infinite series over here. It is fairly complicated, but the only thing that matters in deciding convergence is how does this term over here behave when n becomes very, very large. So let's look at the numerator and the denominator separately. The numerator is 1 plus 2 sine n theta plus sine squared n theta, and certainly sine of theta is less than 1, so is sine squared of n theta less than or equal to 1, and so this whole thing is less than or equal to 4. Look at the denominator. That's 3 to the n plus 5n squared. And since n is bigger than 1, it could be much bigger than 1, this is certainly bigger than 3 to the n. So take these together, and now let's look at the ratio. So this 1 plus 2 sine n theta plus sine squared n theta divided by 3 to the n plus 5n squared is certainly going to be less than 4 divided by 3 to the power n. Therefore, this infinite series that we are looking at is going to be less than 4 times 1 over 3 to the n, and it really doesn't matter where n starts from. We're only interested in large values of n. But then this is a geometric series, and this is finite. One doesn't really care what its value is, but this is finite, and so this series over here, without knowing anything more, we're able to say that this converges. Now let's look at this series over here, sine of 1 over n. Again, let me repeat that the only thing that matters is the behavior of these terms when n goes to infinity. So when n is large, sine of 1 over n goes as 1 over n. And so therefore this goes as 1 over n. Now 1 over n diverges. And so when we go to very, very large values of n, this sum over here tends to infinity, which means that this will not converge, it will diverge. So the point is that by comparing a given series, this one over here or this one over here, with another series, which either converges or diverges, we were able to figure out the behavior of this series and this series. Let me now come to a second means which will help us decide whether this infinite series actually converges or does not. This test is going to be called the ratio test, and that's because we're going to look at the ratio of the next term of the series divided by the previous term, and if this ratio is less than 1 as n becomes large enough, then this series here will indeed converge. In order to prove this, let me do the following. So this is our original series, n goes from 1 up till infinity of Bn, which I'm not writing. And I'm going to break this up into two parts. So n will go from 1 up till some number n minus 1, and then it'll continue from n to infinity. So I haven't missed out any terms at all. Now, when n is large enough, and so when n is bigger than this large number n over here, then what we'll have is that Bn plus 1 will be less than Bn. And in order to make this more definite, let's say that Bn plus 1 is r times Bn, where this r is less than 1. So r is strictly less than 1, and of course we're only talking about positive numbers over here. So this over here is a finite number. We don't care what it is, but it's just a bunch of terms that have been added together, and it's a finite term. But now let's look at this one over here. N equals n up till infinity of Bn. And so that's Bn plus 1 plus Bn plus 2, etc. Well, let me take Bn common. And in the brackets, I will then write Bn plus 1 divided by Bn. And then Bn plus 2, I'll divide this by Bn plus 1. But let me get rid of that by multiplying by Bn plus 1 over Bn, and so forth. So this is an infinite series. Now the point is that Bn plus 1 over Bn is equal to or less than r. So this here is going to be less than or equal to Bn into 1 plus r squared plus r cubed, etc. And now this is a series that we have learned how to sum. This is in fact just Bn into 1 over 1 minus r. And so therefore this infinite series over here has a sum that is finite, and so provided that r is less than 1, that this condition is satisfied, we will indeed have a convergent sequence. So for the ratio test to work, this is the condition that must be satisfied. To see how the ratio test works out, let's look at a couple of examples. First, let me look at Bn equal to 1 over n. We know that the sum of 1 over n does not converge, but let's see what the ratio test is telling us. Okay, so let me take bn plus 1 over bn, and that's 1 over n plus 1 divided by 1 over n, which is n over n plus 1. And now, as n becomes larger and larger, this will tend to 1. This means that the ratio test does not tell us anything. Well, maybe it will tell us something about this one, 1 over n squared. Actually, we know that this series converges. At least I'm going to show that to you later. But let's see what the ratio test tells us. So here we have bn plus 1 divided by bn. And now the only difference is that I'll have 1 over n plus 1 squared and 1 over n squared. So this gives n squared divided by n plus 1 squared. And then as n goes to infinity, it will again give us 1. So once again, we have learnt nothing. But then let's take an example where the ratio test will tell us something. Take bn equal to 1 over n factorial. In that case, bn plus 1 divided by bn is then 1 over n plus 1 factorial divided by 1 over n factorial. So that makes it n factorial divided by n plus 1 factorial. And this is, of course, 1 over n plus 1 into n factorial divided by n factorial. And that's just 1 over n plus 1. Certainly, that goes to 0 as n tends to infinity. And so, yes, bn plus 1 over bn is less than 1. This is telling us that the series 1 over n factorial converges. In fact, this is the series for e. e to the power 1 is sum of 1 over n factorial, where n goes from 1 up till infinity. So the answer would be 2.73, etc., the value of e. Let me now come to a third test. It's called the integral test and is very useful, and it works even when other tests fail. The question is whether this sum over here, this infinite series over here, converges or not, and the answer is it will converge if the integral of f of x converges. What is f of x? Well, it's defined by the following, that each term of this infinite series can be written as f of n. Let's see why the integral test works, and in doing so, we'll also learn how to prove it. Here is the infinite series that we want to sum, a1 plus a2 plus a3, etc., which I'm going to write as 1 times a1 plus 1 times a2 plus 1 times a3. No harm done in that. Now, I've put over here a1, a2, a3, and so this height is a1, this height is a2, a3. I've also plotted over here f of x, where f of x is defined so that when x is equal to n, then we get an. So this a1 is f of 1, this a2 is f of 2, etc. Now, let me look at the integral of f of x from 1 up till 2. So from here to here, which is the area under this dashed curve here. Similarly, the integral from 2 to 3 of f of x is the area under this dashed curve here, and if I go from 3 to 4, then that'll be under this part of the curve. Now, let's also look at the following. This is height a2 and this is width 1. So this area that I'm shading in is a2. And this area from 1 to 2 also has this portion. Hence, the integral from 1 to 2 of f of x dx is greater than a2. That's pretty clear. Similarly, this is greater than a3, this is greater than a4, and so forth. Now, let me add up all of these areas from 1 to 2, then from 2 to 3, then from 3 to 4, etc. And if I keep going, then I will get the integral from 1 up till infinity of f of x. What we see now is that the integral from 1 up till infinity of f of x is then definitely greater than a2 plus a3 plus a4. In fact, this infinite series here. And so, why don't I simply add a1 to both sides? So I'll add a1 over here and add a1 over here. So then what I get is that the integral from 1 up till infinity of f of x plus a1 is greater than the sum of a_n's from n equals 1 to infinity. And now this is the infinite series whose convergence we are interested in. Here is then our main result. This says that if the integral from 1 to infinity of f of x exists, then this series will also exist because it is less than this integral plus a1. Now, a1 is just a number. It can be anything, doesn't really matter. What matters is that this integral over here from 1 to infinity, and even the 1 doesn't matter. The behavior at infinity is what matters. So, this infinite series will exist if this integral up till infinity exists. Let's see how the integral test works out and helps us decide whether this series over here converges or diverges, and for which values of p. So let me take this integral. Here I have f of x, which I'll take to be 1 over x to the p, and the integral goes from some number a, which is not important, up till infinity. Now, this will be x to the power minus p plus 1 divided by minus p plus 1, and it has to be evaluated between a and infinity. But this result is true only if p is not equal to 1. If it is equal to 1, then we'll have to do this integral separately. Well, let's take p equal to 2. In that case, this now works out to minus 1 over x between a and infinity. At x equal to infinity, of course, this is 0, so we get 1 over a. What we conclude, therefore, is that the sum of 1 over n squared, where n goes up till infinity, so it doesn't matter where it starts from, whether it starts from 2 or 3 or 4, whatever, this is then finite, is less than infinity, and so this series, this infinite series over here, converges. It converges because this integral is finite. In fact, we can conclude even more than just this. We can conclude that 1 over n to the p, where the upper limit is infinity, converges provided that p is greater than 1. If it's greater than 1, then what we'll have over here is 1 over x to the power p in the denominator. When x goes to infinity, that will be 0 and we'll get a finite result. And so this result, this important result, has got from the integral test. What about this? If I have dx over x, well, let me take the integral from a to infinity again. But this integral, we know, is the logarithm of x, And when we evaluate it between a and infinity, this over here is infinity. So we conclude from here that the sum of 1 over n does not exist, that in fact it diverges. And this is what we had seen earlier. So certainly the integral test is consistent with what we saw then. Let's now ask whether this series exists, 1 over n log of n squared. Certainly 1 over n does not converge, but maybe this might. Let's see. So let's look at this integral, 1 over x log of x squared. And we'll take the integral from any number a up till infinity. To solve this integral, let's make a change of variables. Let's call u as log of x. In that case, du is dx over x. So we can replace dx over x that we have over here with du, getting this result. Integral du, 1 over log of x squared, but log of x is u, so that's du over u squared. Let's see where the integrals go from. When x is equal to a, u is equal to log of a. So that'll go from here. When x is infinite, then u is infinite because log increases with x. And so that's infinity over there. We can write this out. This is minus 1 over u evaluated between infinity and log of a. And now at infinity u, or rather 1 over u will be 0, so the answer is just 1 over log of a. And so, yes, this series over here converges. But note one thing. If we didn't have log of n squared and had simply log of n, then we wouldn't have the 2 over here, which means we wouldn't have the 2 over here. And so if we did this integral dx 1 over x log x from a to infinity, this would be infinity. And so this series, this infinite series, 1 over n log n, would diverge. It's clear that squaring log of n made this series converge. If you didn't put that, then this series here would diverge just as 1 over n diverges. I'm now going to discuss infinite series where the terms within that series change sign from positive to negative, back to positive, and so forth. So, suppose that there is a series a1 plus a2 plus a3, and this is an infinite series that keeps going. So that is this series here. Now, if the magnitude of a1 plus the magnitude of a2 plus the magnitude of a3 can all be added up to give a finite result, in other words, if this series converges, then we say that this series here, that is of ANs, is absolutely convergent. Here is an example of an absolutely convergent series. 1 minus 1 over 2 plus 1 over 4 minus 1 over 8 plus 1 over 16th minus etc., which you could write as minus 1 to the n plus 1 into 1 over n squared. On the other hand, if you take the magnitudes of this, you get 1 plus 1 over 2 plus 1 over 4 plus 1 over 8 plus 1 over 16th, etc. And that is 1 over n squared. We know that this exists, and so therefore this series over here is absolutely convergent. So it's absolutely convergent. On the other hand, If I was to take this series, 1 minus a half plus a third minus a fourth plus a fifth minus a sixth, etc., this then is minus 1 to the n plus 1 over n. And now we do know, we've already seen that this series, which is the sum of 1 over n, diverges. So, this is a series that is not absolutely convergent. Actually, this series, 1 minus a half plus a third minus a fourth plus a fifth, etc., converges. If you add up all these terms, it does go to a limit, but it is not absolutely convergent, meaning that if you take the magnitudes, you remove the minus signs, you just add them together, then that sum diverges. So far, absolute convergence has just been a word, just a definition. But now let me show you why it's actually important. And let me go back to the series that you just saw. 1 minus a half plus a third minus a fourth plus a fifth minus a sixth. And I'm sorry I have to write so many terms, but it's actually important because I'm going to show you something that's rather fishy. This, of course, keeps going. Let me call this sum S. So S is the sum of this alternating series. It is not absolutely convergent. And now I'm going to play games with this. I will write this as 1 minus a half, separate this off, minus a quarter, so that's from here, plus a third, minus a sixth, separate that off, minus an eighth, plus a fifth, minus a tenth, minus a 12th, and then 1/7 minus 1/14, minus a 16th, and so forth. Now here the pattern is 1 positive term and 2 minus ones. So 1 positive, 2 minus ones, and so forth. We now write this as half minus a fourth plus a sixth minus an eighth plus 1/10 minus 1/12 plus 1/14 minus 1/16, and this keeps going. Okay, so let me pull 1 over 2 out from here. That makes it 1 minus a half plus a third minus a fourth plus a fifth, and now you see where we are going. But what's over here is what we had started off with. That's S. So we get half S. I start from S and I get half S. How can that be? That is indeed very strange. But what we have learned now is that one cannot rearrange terms in an infinite series unless that series is absolutely convergent. So unless there is absolute convergence, you cannot just make sub-series from this main series over here. You cannot reorder the terms. In fact, there is a theorem that I'm not going to prove, that you can take a series like this, one which is not absolutely convergent, and you can make it give any answer that you want. For infinite series, where the terms change sign from positive to negative, back to positive, and so forth, there is an important theorem due to Leibniz. The theorem states the following. If I have a series like this, A1 minus A2 plus A3 minus A4 plus A5 minus A6, and this series is an infinite series, it continues. This will converge if A2 is less than A1, A3 is less than A2, and if there is this sequence of A1 being greater than A2 being greater than the nth one, and of course each one of these A's is positive. So even if this is not absolutely convergent, it is still convergent. This is why this series, 1 minus a half plus a third minus a fourth, etc., this does converge, even if it does not converge absolutely. Unfortunately, we will not have time to prove Leibniz's theorem, but let's look at some examples. Here are a couple of series, and we'll use the theorem that you just saw, Leibniz theorem, on the basis of which we'll decide whether this series here converges or not. Now, if you look at log of n divided by n, then as n increases, log of n increases, but we know that logarithm of n increases much, much slower than n, and so when n goes to infinity, this goes to 0. You can check using L'Hopital's rule. So if you write log of x over x, well, if you take the derivative of log of x, you get 1 over x. If you take the derivative of x, you get 1. And of course, this goes to 0 as x goes to infinity. And so this series will indeed converge. We saw that all the conditions for Leibniz theorem are fulfilled because each of the A's is positive. Log of 2 over 2 is positive, log of 3 over 3 is positive, etc. The logarithm being positive, provided that n is bigger than 1. Furthermore, the A's are decreasing as n increasing. We saw that. In fact, the limit is 0. That fulfills this condition. And so, therefore, Leibniz theorem tells us this does converge. Next, let's see what Leibniz theorem has to say about this series over here, where an is n to the n divided by n factorial. Of course, this is an alternating series. The signs are changing from positive to negative. But is this going to go to 0 or is this going to blow up? To decide that, let's write it in the following way. So n times n times n times n, and this will be written n times. Let's divide this by n factorial. So n factorial is n into n minus 1 into n minus 2. So wherever there's an n, we'll put something below that. And finally, it comes down to 1. So there's the same number of numbers above as below. Now, obviously, each one of these numbers, n over n minus 1, n over n minus 2, etc., is bigger than 1. So we are multiplying a large number of numbers, each of which is bigger than 1, and so this goes to infinity. Therefore, this series will not converge. Instead, it will diverge. There is a lot more that can be said about the convergence of series, and I have not even touched upon the subject of uniform convergence. What that means is that you could have a series which has an additional parameter to it. And for certain values of the parameter, the series will converge very well. For others, it will not. But that gets us into a new subject, that of uniform convergence. And we've reached the end of the 30th lecture. So sorry, we'll have to stop just here. And good luck in your studies.